Okay, I wanted to address some of the kind of troubleshooting stuff that people have been encountering. Stuff that I encountered when I was doing this myself, and yeah, hopefully this will help. So first things first, there is a rather helpful announcement buried deep in our class. So these are obviously current for all intents and purposes. If you keep scrolling back, you should see a bunch of other things. And if you scroll all the way back to this one, this was one that I got a few emails about. And the same thing happened to me. And I'll show you what it means physically. I took some pictures and put it on my computer. So this is an issue if you are measuring, I can't highlight on an announcement. If you are measuring like 3 volts everywhere, 3.3 volts, really. You should be measuring like something close to 0 and something close to 3. And by that, I mean, let me head over here. So this was what happened when I put my probe on the, nope, not that one. Right, so here's my setup, right? So this one is connected to 3.3. So that means if I put my probe anywhere on there, it should read 3.3 volts because it's directly connected to it. And through the whole objective of the lab is that this kind of conductive paper brings that voltage or potential all the way across the thingy. Likewise, here, this is connected to ground, and that means all of that should be 0 volts. So putting the probe anywhere on there should be good. That was what I messed up, and that is exactly what this announcement is talking about. You have to make sure that the metal is touching the tape. Mine, I thought was taped down, but it actually looked like this. So here, this one looks, flatly taped down. That's my 3.3. This was what my ground looked like as soon as I read that. And I was like, oh, that kind of makes sense. It's not connecting. The other aspect of so this, you could have anticipated this. Well, no, not really. But there are other ways that comes up. So if you read the very first, no, not the very first, slide 1, slide, is that even, no, that's the theory part. I'll get to in a second. The limitations, we're supposed to be envisioning, like the ideal setup would be if those conductive strips went forever. And that way, like if we were to measure over here, things wouldn't look like they do in here. So that would end up being, yeah. So things end up, curving around when you have this finite part here. Anyway, let me go back. Here, copper tape makes for poor electrical contact with the paper. Not great. The paper is not particularly uniform in its resistivity. So an example of that, let me see if I have anything over here, show you. Yeah, this is kind of related. So yeah, this was after I fixed it. I just grabbed more of the tape wherever it went and made it more like this one. And I'll mention this in just a second. So the reason for more, like the whole point we're using the breadboard is to make the wire in which we probe longer. And so I was like, oh, okay, I'll plug one into this and one into this end because they told me it was connected. One thing I didn't realize is that as charge travels over a surface, it dissipates. So that's the whole draw that people have for superconductors, because in a superconductor, there is no energy dissipation. You can harvest solar energy in Arizona and pipe it through a wire to New Jersey, and no energy is lost. But you can't do that with real power. That's why like power is generated at a power station and then it serves the surrounding community. Because as it goes through the pipe, we don't have amazing pipes. or wires or whatever. And so it doesn't always work. So this is one aspect of that. The way it manifested itself for me was that my values here, like all these ones, like the circle ones, were different than here. And so what we expect before we even do the lab is this is at some potential. It's at 3.3 volts. This is at 0 across the whole thing. And so the way we think about that is increased potential means it's higher up. So like this is my, what is that, green? Yeah, so this is the one with 3 volts. The other one is at 0. So let's just say this is like sea level, and this is some ledge. And envisioning like my arms are infinite, the slope between those two things is exactly what the electric field would be. So as we go a little bit down and a little bit down, anyway, what I'm trying to say is this potential value should be the same as this potential value and this potential value and this. So those values should roughly all be the same, because that is the same. And so is this. So what we should see once we make our graph for this parallel plate part is a surface. So like it should be basically just a ramp. It's a ramp. And so I didn't see that. What I saw at first was this. So this was closer to this part. So it was reading things stronger than it was here. And that's when I retaped this. That had already been retaped. And instead of getting maximum reach out of this thing by plugging one in here and one in here, I was like, okay, this system is clearly not perfect. Let's put these two immediately close to each other. And that's when I got, so that was my first data. It's hidden a little bit. And this was my second data. So much more uniform, 2.1, roughly 2.1 across the whole top row. So that when I mean top row, I mean this one. And I should have known, right? Because if this is 3 volts and this is 0 volts, and these are all equally spaced, they should be like, this should be, I don't know, 0.5, 1, 1.5, 2, or just like some kind of, I don't know what 3.3 divided by 5 is, but yeah, you get the point. So I did see that with this. So those things are roughly equal, these are roughly equal, and these are roughly equal. So you see like this was not equal to this. So I have this weird behavior going on here. So I discarded this. The next thing I did, so once I highlighted that and I did the 3D surface, this graph looks awful. Like I can't tell anything that's going on. So a few things I did. I got rid of the legends because who cares? Doesn't really matter. Honestly, the only thing that matters is this. That's what the potential is. So yeah, I'm just gonna get rid of all these. And when I say get rid of, I'm just pressing the backspace button, in case you were wondering. Then I can right click in the plot area. And for 3D rotation might do it too, but I can get to it this way. 3D rotation, and instead of 20, I'm just gonna, I guess 90 is fine. Click OK, and use, whoa, where'd it go? There it is. So now you see that it's showing me that gradient that I want. But my data does not, this is like the 0.7 to 0 thing that was mentioned in the lab manual. I know what the floor is. Or no, actually I want to click on this, the vertical axis, format the axis. And let's see, my data starts at like 0.7. And it ends at like, that's fine, 2.2. And if I want more colors, I can do 0.2 for more colors. So yeah, that's exactly what I visualized, which was something of high potential, something of low potential. And because we're hoping that it's uniform in between, this is my second piece of data there, and so forth. And the way you can view that in terms of like what this means is like, if you were to put a positive charge, which is called like a test charge, if you were to just drop a positive charge in this situation, what would happen? It would roll down. So that's what it means. Like you'll get into like Coulomb's law and things like that. The electric field always points away from a positive charge, so it points either to infinity or to a negative charge. We don't have a negative, but you can imagine if we had done like 3 lines, like 3.3, 0, and negative 3.3, it would like positive charges go to negative charges and away from other positive charges. Repulsion. Yeah. The other question I got at the very end is with regards to this point, where I was mentioning like what are all the values when you actually put your little probe on these sheets? And that I will link another YouTube video which talks about the concept of conductors. And it's a really nice textbook that I go through. It's called Griffith's. It's like Introduction to Electrodynamics or something. And so this is just called conductive paper or conductive tape, conductive paper throughout the whole lab. But the more general class of materials is called a conductor. So yeah, let me know if that helps, and I will, I don't know, do more if it's done.